Hello everyone, I am Liam, back with another episode of LRN STEM, and in this episode I'm going to give you an overview of the most beautiful part of math that I know. And that part of math is fractals. In this episode of LRN STEM, I plan on discussing what makes a fractal, why are fractals so special, what can fractals be used for, and then in the last part I want to give you a compilation of the most beautiful math that I have found on Desmos. And that will be in a compilation at the end, so stay tuned, keep on watching. So, what is a fractal? So, a fractal is basically just a paradox, but it is a paradox in which a fractal has a finite area, but an infinite perimeter. You may be familiar with the Mandelbrot set, or Mandelbrot, I do not know how to say it. But, generally, I'll give you a more specific look on how it actually looks on the screen. But, the Mandelbrot set is basically a fractal in which it has symmetry along this line, and that line only. And then when you zoom in, parts of this fractal, like let's say we zoom in here, along this line, it will have parts of the fractal which just continually get smaller, and it continually gets more specific, giving the infinite perimeter for a finite area. And the Mandelbrot set is known for being the world's most famous fractal, not only for its beauty, but for the ease of its construction, as it just uses imaginary numbers and repeating sets, as it gets more and more specific, as we'll see later on Desmos, it starts out in a circle, but then as it gets more and more complicated, or more and more additions are added to the function, which are not really a function, it slowly creeps in to the actual perimeter or area of the Mandelbrot set. Just like that. And then the Mandelbrot set is so well known, but also it has two main areas that are of a special wide significance. So right here is where, I did not draw it perfectly, but in actuality, there is basically, they just barely touch this circle and then this half of the Mandelbrot. So right here, along right here and right here is what is known as a seahorse's tail, because as you zoom in, it resembles a seahorse's tail just like it does in real life. And right here, as I showed you earlier, this is called the elephant's bum, for obvious reasons. For every part that you zoom in on the Mandelbrot set, it will never fully show the perimeter of the function as it is indefinite. So whenever you zoom in, it always becomes smaller and smaller. Well, it still shows the same amount of complexity, which increases forever. However, even though the Mandelbrot set is the main fractal that most people know, there's also numerous other fractals, such as this one, which is known for its simplicity. This fractal consists with just having a line that separates into two lines, which separates into two lines, and into two lines, into two lines, into two lines. It simply is just a tree, which many saw how trees keep on splitting. So Newton discovered this self-similarity in trees and how every time they grow a new branch, it splits. However, there's also other fractals such as the Koch snowflake, if that's how you say it again. It starts off with a triangle, then you add triangles on its sides, triangles on its sides, and then triangles on its sides, on its sides, on its sides. Then, by the third time that you're adding triangles, you'll already have to add 48 triangles. It is quite insane how fast these fractals divulge into an insane amount of perimeter to already add up, but the area for this is quite easy to actually find. So this area on the bottom is S. So when you need to find the area, from a complex amount of computations that you need to find, it can actually just be simplified to 2 square root of 3 over 5 times S squared. And that is the entire area. Ultimately, these fractals did not just become popular for their beauty, but some even thought that fractals had a higher meaning hidden inside of them. Shown above is the image created when taking the escape count, or number of the squares an operative receives, and it determines its location on the 15 by 15 pixel graph. However, some still say that because the Mandelbrot function or other fractals can become so complicated that their functions can give an infinite number of ways to be identified as similar or repetitive in their nature, you can find any function in the Mandelbrot set of equations to graph anything that you want. Except the only downside of this is that you just need to find it. However, some say that because a fractal is so complicated, one can simply just find a right equation to display whatever they want, negating the specialness of the image that you just saw. Put simply, it's merely up to the luck of finding the right equation to produce the image that you want to find. When scientists and mathematicians have dived very heavily into the imaginary numbers that compose the Mandelbrot set, they have found that the sets of functions that comprise the Mandelbrot set actually replicate some types of galaxies that have been found in the regions of outer space, and also it has replicated probability vectors that have been seen in quantum mechanics and quantum physics. Besides the massive implications that the Mandelbrot set has already found in the depths of science and space, it has also massive implications in the world that we live in, Earth. Louis Fry Richardson, an English mathematician and cartographer, he wanted to find the area and perimeter of England, but he had a slight problem. When he measured the area in perimeter of England with kilometers, meters, or centimeters, he got vastly different results. Okay, so let's pretend that that is England, or the UK. When we measure it with, let's say, the largest measurement that we have, let's say that our measurement comes out to a box. But when we go smaller, we get an area like that. Then we go even smaller. We get an area like that until the lengths of the measurements get so small that we get the actual area. Similarly, this is just how a student would be introduced to calculus or integration in their first calculus course. Through the use of Riemann sums, a way to divide up the area underneath a curve until that area divided up gets so small that we get the actual area under the curve. This I will show you on screen. Shown on screen, Riemann sums were a way to get an estimate at the area under a line. By dividing the integral's length into a set number of lengths, one can guess at the proposed area by hand using sigma sums. However, due to the large length of these segments, eventually you can take the limit of these sums. As the change in x becomes so small, the accurate area under the curve is found. So, when evaluating England's area with kilometers, you may gain some area in some places but leave some out in others. The same happens with the smaller and smaller units of measurement that you use, but the excess/unexcess, if you will, gets increasingly negligible. In integration, an equally beautiful aspect of math, as it links differentiation, antiderivatives, and limits into two set rules, you eventually get the integral of capital F of x times d of x to find such an area. And for the perimeter of a function, you can take the integral of the derivative of the function f derivative of x times d of x. However, integrating and finding the perimeter of a fractal would lead you to have some problems. The highest on the list of these problems is that the integral is not a function. A fractal for its one input has many outputs correlated to that one specific and unique input. And B, a fractal uses imaginary numbers in order to be able to be graphed. This is not actually what a function uses, as it needs real numbers to be plotted. To even start integrating to find the area or perimeter of a fractal using traditional integration techniques, you would have to start by using the Lebesgue integration technique. However, the amount of math that would go into Lebesgue integration would make the title of this video not be true, as the amount of math might scare some of you away. Me too. Thankfully, we do not have to do this ourselves, as the group Ewing and Schober have done this for us, calculating almost 240,000 sets of equations to give us an approximate area is less than 1.7274, but it should be around 1.66 to 1.71. Newer methods of calculating the area of the Mandelbrot set have led to the area of the set obtained by pixel counting is 1.50659,177 plus or minus 0.000000008 to a 95% certainty. They accomplish this by having an algorithm calculate the number of pixels on screen at one time, and then by zooming in, it calculates the fractions of pixels present, and then on and on and on until it gets so insignificant that the actual area is found. Now that we know that there are methods to calculate the area and perimeter of fractals, and how we might even possibly understand the Mandelbrot set, or God's fingerprint, now I wanted to show you all a very relaxing compilation of the most beautiful math that I've found on Desmos in YouTube. So let's take a look.